What if we could peer into the darkness of space and see the birth of the universe? What if a telescope could unlock the secrets of stars and galaxies that formed billions of years ago, offering us a glimpse into the very beginning of time? The James Webb Space Telescope, JWST, the most advanced space observatory ever built, is designed to do just that. Born from decades of scientific ambition and collaboration between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, JWST represents a quantum leap in our ability to explore the cosmos. It will allow us to observe the earliest galaxies, understand the formation of stars and planetary systems, and even search for signs of life on distant exoplanets. While previous space telescopes like the Hubble have expanded our understanding of the universe, they have also revealed just how much more there is to learn. With its revolutionary infrared capabilities and unprecedented size, JWST promises to take us further than we've ever gone before, answering fundamental questions about the origins of the universe and our place within it. This is more than just a scientific mission. It is a journey into the unknown, a window to the deepest mysteries of the cosmos. The idea of a successor to the Hubble Space Telescope began to take shape in the early 1990s, when it became clear that Hubble's capabilities, while revolutionary, were not enough to answer some of the deepest questions in modern astrophysics. Hubble's visible light observations had already provided us with breathtaking images of the universe, but it was limited in its ability to explore the farthest reaches of space, particularly when it came to observing objects hidden behind dust clouds or studying the earliest moments after the Big Bang. What scientists needed was a telescope capable of observing in the infrared spectrum, one that could peer deeper into the universe and further back in time. The concept for the James Webb Space Telescope, JWST, began to crystallize as a collaborative effort between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. The vision for JWST was ambitious. It would need to be large enough to collect vast amounts of light, yet compact enough to fit into a rocket for launch. It would also need to operate in the harsh environment of space, beyond the protective reach of Earth's atmosphere, and withstand extreme temperatures as it would be positioned at the second Lagrange point, L2, about 1.5 million kilometers from Earth. Thus, the journey of JWST was marked from the very beginning by challenges that would test the limits of engineering, design, and international cooperation. The development of the JWST was not without its hurdles. The complexity of the project, both in its technological requirements and financial demands, resulted in numerous delays and cost overruns. The telescope's size was a fundamental challenge. Its primary mirror, which spans 6.5 meters, is more than 2.5 times larger than Hubble's. This mirror needed to be constructed from 18 hexagonal segments that would later be precisely aligned once in space. To transport such a large mirror, it had to be folded for launch and would only unfold once in space, a process that required flawless engineering and deployment techniques. In addition to its mirror, JWST required an innovative sunshield to protect its instruments from the heat of the sun. The telescope's infrared detectors could only function at extremely low temperatures, and the sunshield, about the size of a tennis court, was designed to block sunlight, stabilizing the temperature and ensuring optimal performance. This, in itself, was a monumental engineering task, as the shield had to be deployed in the vacuum of space with perfect precision. The financial and logistical aspects of the project also posed significant challenges. What began as a relatively modest $500 million project in the 1990s soon ballooned in cost, reaching over $10 billion by the time of its planned launch. Despite the astronomical budget, delays in the construction and testing phases stretched the timeline of JWST's launch for decades, with initial plans aiming for a 2007 launch, but the actual launch not occurring until December 2021. One of the central reasons JWST was conceived was to take advantage of infrared astronomy, a field that had long been considered a key to unlocking the secrets of the universe. Unlike visible light, which is easily blocked by cosmic dust, infrared radiation can pass through these barriers, allowing astronomers to observe stars and galaxies that are hidden from view in other wavelengths. This made infrared observations critical for studying the earliest periods of the universe, especially galaxies and stars that formed during the first few 100 million years after the Big Bang. The telescope's infrared capabilities also allowed scientists to investigate the formation of planetary systems, including our own. By observing the heat emitted by dust and gas around young stars, JWST could offer new insights into how planets form and evolve. Furthermore, the telescope's ability to observe distant exoplanets, their atmospheres, and their potential for habitability would bring us closer to answering one of the most profound questions in science. Are we alone in the universe? The design of the James Webb Space Telescope was an exercise in pushing the boundaries of engineering. To achieve its scientific goals, the telescope had to be powerful, precise, and capable of operating in the extreme conditions of space. At its core, the JWST is composed of several key components: the primary mirror, the sun shield, the instruments, and the scientific payload. At the heart of the JWST is its large 6.5-meter primary mirror, which is more than 2.5 times the size of Hubble's 2.4-meter mirror. This mirror is made up of 18 hexagonal segments, each about 1.32 meters across, designed to fit together like pieces of a puzzle. The segments are made of a lightweight but durable material called beryllium, coated with a thin layer of gold to optimize infrared light reflection. The reason for this large mirror is simple. The bigger the mirror, the more light it can collect, allowing the telescope to observe faint and distant objects that would otherwise be invisible. The mirror's design was revolutionary in another way. Its segments needed to be folded for launch to fit inside the rocket. Once deployed in space, these segments would be carefully aligned, a task requiring incredible precision. Each of the 18 hexagonal segments is adjustable, allowing for precise alignment to form a single, unified mirror capable of capturing detailed images from the farthest reaches of the universe. Another key feature of JWST is its 5-layer sun shield, which is about the size of a tennis court. The sun shield's primary purpose is to block sunlight, keeping the telescope's instruments at the incredibly low temperatures needed for infrared observations. The telescope operates at temperatures below -220 degrees Celsius, far colder than most spacecraft, and the sun shield is critical in achieving this. Made of a special material called Kapton, which is both heat-resistant and lightweight, the sun shield shields the telescope from the sun, Earth, and Moon, which are all sources of infrared radiation that could interfere with the observations. The sun shield's deployment in space was a complex process, requiring a series of steps to unfold and tension the 5 layers. This delicate operation, which took several days to complete, was one of the most high-risk aspects of the JWST's deployment. The sun shield must be deployed with flawless precision to ensure that the telescope remains at its required operational temperature. The scientific payload of JWST consists of 4 main instruments: the near-infrared camera, NIRCam, the near-infrared spectrograph, NIRSpec, the mid-infrared instrument, MIRI, and the fine guidance sensor/near-infrared imager and slitless spectrograph, FGS/NIRISS. Each instrument is designed to capture different wavelengths of infrared light, allowing scientists to study a wide variety of celestial phenomena. NIRCam is designed to study the formation of the first galaxies, stars, and planets. It will capture detailed images of these objects, providing a look at the universe's early history. NIRSpec is a spectrograph that will analyze the light from distant galaxies, enabling scientists to determine their composition, temperature, and motion. MIRI is the most sensitive instrument on JWST and is designed to study the coldest and most distant objects in the universe, including the first galaxies and supermassive black holes. HES/NIRASS is used for precise pointing and astrometry, ensuring the telescope remains aligned during observations. It also has the capability to study exoplanets by analyzing their atmospheres and looking for signs of life. These instruments are all carefully integrated into the spacecraft, allowing the telescope to operate as a cohesive unit. Each instrument was tested rigorously to ensure it could withstand the extreme conditions of space and perform with the required sensitivity. The technology behind JWST is truly groundbreaking. Perhaps the most important technological advancement is its ability to observe in the infrared spectrum, which requires advanced detectors and cooling systems. The telescope is equipped with specially designed infrared detectors that are sensitive enough to detect the faintest signals from distant objects. The adaptive optics and calibration systems are also central to the telescope's capabilities. JWST's mirrors must be aligned with extreme precision to avoid blurring the images it captures. Each of the 18 hexagonal segments is individually adjustable, and their positions are fine-tuned through a complex system of motors and sensors. These adjustments must be made in space, where there is no chance to fix errors, so the alignment system was designed to be extremely accurate. JWST also uses a unique cooling system to maintain the extremely low temperatures necessary for infrared observations. The cooling is achieved through passive means, such as the sunshield, and active systems, like a special cryocooler for the MIRI instrument, which needs to be kept colder than the rest of the telescope. These systems work together to maintain the telescope's sensitivity, ensuring it can capture the faintest infrared signals from distant stars, galaxies, and exoplanets. The deployment of JWST was perhaps the most delicate part of the entire mission. Unlike earlier space telescopes, which were assembled and tested in Earth's orbit, JWST had to be folded tightly to fit into its launch rocket. This meant that its deployment had to be done in space, requiring a series of highly complex and carefully orchestrated steps. Once launched, JWST began its journey to the second Lagrange point, UL2, where it would spend its operational life. Upon arrival, the telescope began to unfold, starting with the solar arrays that provided power to the telescope. Next came the sunshield, which was carefully unfolded and tensioned. Each layer had to be pulled taut to prevent any wrinkles or folds that might block its effectiveness. After the sunshield was fully deployed, the telescope's mirrors were then gradually aligned, with each of the 18 mirror segments adjusting to form a unified whole. This process took several months, as the telescope was calibrated and tested. The final step was the activation of the instruments, each of which had to be cooled to the proper temperature and calibrated for optimal performance. Despite the complexity and risk, the deployment process was a resounding success. Each step of the deployment, from the unfolding of the sunshield to the alignment of the mirrors, was carried out with incredible precision. This flawless deployment was a testament to the dedication and expertise of the teams involved in the mission. The James Webb Space Telescope is not just a marvel of engineering. It is also a powerful scientific tool designed to answer some of the most profound questions in astrophysics. Its advanced infrared capabilities and large mirror enable scientists to peer further back in time and space than ever before, uncovering details about the universe that were previously out of reach. From studying distant galaxies to investigating exoplanets, the science behind JWST's mission is both ambitious and transformative. In this chapter, we will explore the key areas of research that JWST will revolutionize: distant galaxies, star formation, exoplanets, and the mysteries of dark matter and dark energy. One of the most exciting capabilities of JWST is its ability to look back in time, far beyond the reach of Hubble or any other telescope before it. The infrared sensitivity of JWST allows it to observe the earliest galaxies that formed just a few 100 million years after the Big Bang, more than 13 billion years ago. These galaxies are far too distant to be seen with visible light, as their light has been stretched into the infrared by the expansion of the universe. By studying these distant galaxies, scientists hope to understand how galaxies first formed, how they evolved over time, and how the first stars and black holes came into existence. JWST will be able to capture light from galaxies that existed during the cosmic dawn, a critical period in the universe's history when the first stars and galaxies emerged from the dark ages of the universe. By observing the faintest signals from this era, JWST will allow astronomers to witness the formation of galaxies and star clusters in real time, providing insights into the processes that shaped the structure of the universe as we see it today. The telescope's high resolution and ability to detect faint infrared light will allow astronomers to study the details of galaxy formation and the interactions between galaxies. By observing the most distant galaxies, JWST could also provide clues about the reionization epoch, a period in cosmic history when the first light from stars and galaxies began to ionize the hydrogen gas that filled the universe, allowing for the universe to become transparent to light. Another key area of scientific inquiry for JWST is the study of star formation. Stars are born in vast clouds of gas and dust, and JWST's infrared capability makes it uniquely suited to observe these regions of space. Visible light is often blocked by cosmic dust, but infrared radiation can penetrate these dust clouds, revealing the process of star formation in incredible detail. JWST will be able to observe some of the most famous stellar nurseries in the universe, such as the Carina Nebula and the Eagle Nebula. These nebulae are home to massive, young stars that are still in the process of forming. By studying the light emitted from these regions, JWST will provide astronomers with detailed images of young stars, protoplanetary disks, and the complex interactions between gas and dust. This data will help researchers understand how stars form and evolve, and how the ingredients for planet formation are assembled in these early stages of stellar life. In addition to studying star formation, JWST will also observe the processes of stellar death, such as the evolution of red giants and supernova. By studying these processes, scientists can gain insights into the life cycles of stars and their role in enriching the universe with heavier elements that are essential for life as we know it. One of the most groundbreaking aspects of JWST's mission is its ability to study exoplanets, or planets outside our solar system. Since the discovery of the first exoplanet in 1995, astronomers have uncovered thousands of these distant worlds, but studying them in detail remains a significant challenge. JWST is poised to revolutionize the study of exoplanets by using its advanced infrared instruments to observe their atmospheres, detect their compositions, and search for signs of habitability. Using its near-infrared spectrograph, NIRSpec, and mid-infrared instrument, MIRI, JWST will analyze the chemical composition of exoplanet atmospheres by measuring the absorption and emission spectra of light passing through or reflecting off them. These spectra can reveal the presence of key molecules such as water vapor, methane, carbon dioxide, and oxygen, molecules that could indicate the potential for life. JWST will also be able to study exoplanets in unprecedented detail, characterizing their size, mass, and orbits. The telescope's ability to observe transiting exoplanets, where a planet passes in front of its host star from our point of view, will allow scientists to study the atmosphere and surface conditions of these worlds in ways that were previously impossible. Beyond searching for Earth-like exoplanets, JWST will also study extreme worlds, including gas giants, super-Earths, and planets located in the habitable zone, the region around a star where liquid water could exist on the surface. By expanding our knowledge of exoplanetary systems, JWST could eventually help answer one of the most profound questions of our time. Are we alone in the universe? While JWST's primary mission is focused on studying the visible universe, it is also equipped to explore some of the most elusive phenomena in modern cosmology: dark matter and dark energy. These two components make up most of the universe's mass energy content, yet they remain largely mysterious. Dark matter, which interacts with gravity but not with light, can only be detected through its gravitational effects on visible matter. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe, but its exact nature is still unknown. JWST's high-resolution observations of galaxies, galaxy clusters, and large-scale structures will provide new insights into the distribution of dark matter in the universe. By studying how light is bent and distorted by gravitational lensing, a phenomenon caused by the presence of massive objects like galaxy clusters, scientists can map the distribution of dark matter in the cosmos. These observations will allow astronomers to test current theories about the nature of dark matter and potentially uncover new clues about its composition. Similarly, by observing the growth and evolution of galaxy clusters, JWST will help researchers understand the role of dark energy in the expansion of the universe. The way galaxies and clusters interact over time is influenced by dark energy, and by observing these processes in great detail, JWST could shed light on the fundamental forces that drive the universe's evolution. When the James Webb Space Telescope, JWST, launched on December 25, 2021, the world eagerly awaited its first images. For decades, scientists, engineers, and space enthusiasts had worked tirelessly to bring the most powerful space observatory ever built into existence. And when the moment finally came, it did not disappoint. The first images sent back by JWST were nothing short of revolutionary. These images, captured from the farthest reaches of space, revealed not only the telescope's extraordinary capabilities, but also the incredible beauty and complexity of the universe. In this chapter, we will explore the historic first images of JWST and their profound implications for science and humanity. After months of testing and calibration, the first images from JWST were revealed to the public on July 12, 2022. The images were so striking that they immediately captivated the world's attention, offering a glimpse into a universe that had remained hidden from view until now. The most famous of these initial images was the SMACS 723 Deep Field, a breathtaking view of a galaxy cluster located over 13 billion light-years from Earth. This image was not only the deepest infrared image ever taken, but also the most detailed, showcasing thousands of galaxies, some of which existed just a few 100 million years after the Big Bang. The level of detail in this image was unprecedented, with individual galaxies, star clusters, and even distant supernova clearly visible. Another iconic image was the Carina Nebula, a stunning view of a region where new stars are forming. This image revealed thousands of stars in various stages of formation, many of them surrounded by massive gas clouds. The image's clarity and depth allowed scientists to observe the birth of stars and the processes that lead to the formation of planetary systems, offering unprecedented insights into the early stages of star formation. The Southern Ring Nebula was also among the first images released, showing a dying star surrounded by an intricate cloud of gas and dust. This nebula, which had been observed previously by Hubble, was now revealed in a completely new light, showcasing intricate details that had never been seen before, including the star's central mass and the surrounding shells of gas it had expelled over millennia. In addition to these stunning deep space images, JWST's first images also included its observations of exoplanets. The spectrum of the exoplanet WASP 96 bits, captured by JWST's near-infrared spectrograph, NIRSpec, showed a detailed analysis of the planet's atmosphere, revealing the presence of water vapor and other gases. This breakthrough represented a major step forward in the study of exoplanets, demonstrating JWST's ability to directly analyze the composition of distant worlds. These first images were not just scientific triumphs. They were also a symbol of the incredible human effort and collaboration that went into creating the telescope. They marked the beginning of a new era in space exploration, one in which we could see the universe in greater detail than ever before and answer questions that had once seemed far beyond our reach. The first images from JWST were not only visually stunning, but they also revealed a wealth of scientific information that is still being analyzed by researchers. Let's break down what these images tell us about the universe and the incredible discoveries that JWST will continue to make. The deep field image taken by JWST provided the most detailed look at the distant universe ever captured. By observing a galaxy cluster, JWST was able to peer into the early universe, revealing galaxies that formed just a few 100 million years after the Big Bang. These galaxies, some of the oldest and most distant ever observed, appear as faint, reddish blobs due to the stretching of light caused by the expanding universe. The image also demonstrated the power of gravitational lensing, a phenomenon where the gravity of a massive galaxy cluster bends the light from objects behind it, magnifying distant galaxies and allowing JWST to see even further into space. This deep field image will help scientists study the earliest stages of galaxy formation and evolution, providing new insights into how galaxies and stars formed in the wake of the Big Bang. The Carina Nebula, one of the most famous star-forming regions in our galaxy, was imaged in stunning detail by JWST. This image captured the complex interplay between gas, dust, and young stars. One of the most remarkable aspects of the Carina Nebula image was the clarity with which JWST could see through the gas clouds, revealing areas of active star formation. These regions, known as stellar nurseries, are where new stars are born from collapsing gas and dust. The high-resolution capabilities of JWST allowed scientists to observe not only the stars themselves, but also the complex structures of gas and dust that surround them. The image also highlighted the intricate processes of stellar evolution, including the impact of stellar winds and radiation on the surrounding environment. These observations will help scientists better understand the conditions that lead to the formation of stars, planets, and even life itself. The Southern Ring Nebula, a planetary nebula formed by a dying star, was imaged by JWST in breathtaking detail. This nebula is the result of a star shedding its outer layers as it nears the end of its life, leaving behind a dense core that becomes a white dwarf. JWST's images revealed intricate details of the nebula, including concentric rings of gas and dust that were expelled by the star over thousands of years. These structures, previously unseen in such detail, provide scientists with a glimpse into the final stages of a star's life cycle. The images also revealed the complex interactions between the star's radiation and the surrounding gas, shedding light on the processes that shape the evolution of stars and their surrounding environments. The spectrum of exoplanet WSP96 bits provided one of the most significant breakthroughs in exoplanet research. By analyzing the planet's atmosphere, JWST was able to detect the presence of water vapor, a key ingredient for life, along with other molecules, such as sodium and methane. This observation marked the first time that a telescope had been able to directly analyze the atmosphere of an exoplanet with such precision. By studying the atmospheres of exoplanets in this way, JWST opens up the possibility of identifying potentially habitable worlds, offering the first steps toward answering the age-old question, are we alone in the universe? The first images from JWST represent more than just technical achievements. They are a window into the very fabric of the universe. They allow us to peer into the distant past and observe galaxies and stars as they existed billions of years ago. They give us a new understanding of the processes that shaped the universe, from the birth of stars to the formation of planetary systems. And perhaps most importantly, they offer the possibility of discovering new worlds, new phenomena, and even new forms of life. For humanity, these images are a testament to our collective ability to dream big, collaborate across borders, and tackle some of the most complex challenges in science and engineering. They show us what is possible when we reach beyond the limits of our knowledge and pursue the unknown. In this sense, the first images from JWST are not just a triumph of science, they are a triumph of human spirit and curiosity. The advent of the James Webb Space Telescope JWST marks a pivotal moment in the history of human exploration and discovery. While the telescope's scientific capabilities are groundbreaking, its emotional and philosophical implications are just as profound. The images and data that JWST sends back from the farthest reaches of space stir something deep within us, invoking wonder, awe, and even existential reflection. As we peer into the distant past, observing galaxies, stars, and even planets that existed billions of years ago, we are confronted not only with the enormity of the universe, but also with questions about our place within it. In this chapter, we will explore the emotional impact of space exploration, the philosophical reflections sparked by JWST's discoveries, and the profound implications of searching for life beyond Earth. Humanity's drive to explore the unknown is one of our most defining characteristics. From the earliest voyages across uncharted oceans to the first steps on the moon, our curiosity about the world and the universe has fueled countless scientific and technological advances. The launch of JWST is a continuation of this spirit of exploration, but it takes us further than ever before. For the first time, we have the ability to look back in time to the very birth of the universe, seeing galaxies in their infancy and observing cosmic events that occurred billions of years ago. This ability to witness the vast history of the cosmos is not just a scientific achievement. It is an emotional one as well. The knowledge that we are capable of understanding the distant past and possibly the origins of our own existence connects us to something far greater than ourselves. For many, the first images from JWST evoked a profound sense of awe and wonder. The sheer beauty of the images, the vibrant nebulae, the intricate galaxies, the distant stars, captures the imagination in a way that few other scientific endeavors can. They remind us of the vastness of the universe and our relative smallness within it. Yet, paradoxically, these images also bring a sense of unity. They remind us that, despite our differences, we share a common humanity, united in our desire to explore the mysteries of the cosmos. In a world often divided by conflict and discord, the JWST mission offers a rare and powerful reminder of our collective potential and the shared wonder of discovery. The emotional impact of JWST's discoveries extends beyond the scientific community to the public at large. Many have remarked on the sense of hope and inspiration that these images have sparked, particularly among young people. The idea that humanity has created a machine capable of looking so deep into space is a source of inspiration for future generations of scientists, engineers, and dreamers. The emotional resonance of these discoveries cannot be overstated, for they embody the very essence of human curiosity and the drive to reach beyond the stars. One of the most philosophical aspects of JWST's mission is its ability to look back in time, observing galaxies and stars as they existed billions of years ago. When we look into the distant universe, we are not simply seeing what exists now, but rather glimpses of the past, sometimes as far back as the first few 100 million years after the Big Bang. The idea that light from these distant objects has traveled across the vast expanse of space and time to reach us raises profound questions about the nature of time itself. Time, in a sense, becomes a lens through which we view the cosmos. When we observe these distant galaxies, we are seeing them as they were, not as they are. This realization forces us to confront the limitations of our own perspective. The universe is constantly changing, evolving, and expanding, and yet, our observations are inherently tied to the time it takes for light to travel to us. When we look at the deep field images captured by JWST, we are seeing the universe as it was when these galaxies were young, often much younger than our own planet, let alone our species. This perspective brings with it a humbling sense of the passage of time and the fleeting nature of human existence. At the same time, the ability to look back in time allows us to reflect on the origins of the universe itself. The Big Bang, the formation of the first stars and galaxies, the birth of the solar system. These are all moments in the history of the cosmos that we can now observe and study in greater detail than ever before. For many, this offers a sense of connection to the very beginnings of time and space. It reminds us that we are part of a larger cosmic story, a story that spans billions of years and will continue long after humanity is gone. In this way, the JWST's observations prompt us to reflect on the nature of existence, the passage of time, and our place in the grand narrative of the universe. Perhaps the most emotionally charged and philosophically significant aspect of JWST's mission is its potential to answer the age-old question: are we alone in the universe? For centuries, humans have looked up at the stars, wondering whether other civilizations exist beyond our planet. With the discovery of thousands of exoplanets, some of which are located in the habitable zone of their stars, the search for extraterrestrial life has become one of the most exciting frontiers in modern science. JWST is uniquely equipped to search for signs of life on distant worlds. By analyzing the atmospheres of exoplanets, JWST will be able to detect the presence of key molecules associated with life, such as water vapor, methane, and oxygen. These molecules, when found together, could indicate the potential for habitability or even the presence of life. The ability to study exoplanets in this way marks a major breakthrough in the search for life beyond Earth. For many, the idea that we might one day discover signs of life on another planet is both thrilling and deeply philosophical. It raises questions about the nature of life itself, the conditions necessary for it to thrive, and whether life is a universal phenomenon or a rare occurrence. The emotional impact of such a discovery would be profound. The idea that we might not be alone in the universe has the potential to reshape our understanding of life, existence, and our place in the cosmos. It would also force us to confront deeper questions about the nature of intelligence, consciousness, and what it means to be human. If we find evidence of life elsewhere, it may challenge long-held beliefs about the uniqueness of our planet and our species. At the same time, it could offer hope and wonder, as humanity would not only have discovered a new world, but also a new perspective on the possibilities of life in the universe. The discoveries made by JWST also prompt broader philosophical reflections on the nature of existence. As we peer into the universe, we are forced to confront fundamental questions about the origin and purpose of life, the nature of time and space, and the possibility of intelligent life elsewhere. The sheer scale of the universe can be both awe-inspiring and overwhelming, reminding us of the fragility of human life and the transience of our existence. Yet, in the face of this vastness, we also find meaning in our quest for knowledge and understanding. The search for answers to these questions is an inherently human endeavor. It speaks to our desire to make sense of the world around us, to understand our place in the universe, and to seek meaning in the face of the unknown. As we look out into the cosmos, we are reminded that the universe is not just a collection of stars, planets, and galaxies, but a source of inspiration, wonder, and mystery. The discoveries made by JWST will continue to fuel our curiosity, drive our exploration, and inspire future generations to continue asking the big questions about the nature of life and existence. The launch of the James Webb Space Telescope, JWST, is not just the culmination of decades of scientific effort, but also the beginning of a new era in space exploration. With its unparalleled ability to peer into the distant past, study the formation of galaxies, and examine exoplanets, the JWST represents a monumental leap forward in our understanding of the universe. But while its mission will undoubtedly revolutionize our knowledge of space, it is just one piece of a much larger puzzle. The future of space exploration, both in the near and distant future, is brimming with exciting possibilities. This chapter will explore the ongoing missions that complement the work of JWST, the upcoming technological advancements in space exploration, and the long-term goals for the next decades, with a particular focus on the next 20 years, and how the discoveries made by JWST will shape this future. The JWST is a marvel of engineering and science, but it is not the only telescope or mission contributing to our expanding knowledge of the cosmos. In fact, many other upcoming space observatories and missions will work in tandem with JWST to explore different facets of space. These complementary missions will enable scientists to view the universe from multiple angles and gather a broader range of data. One such mission is the Nancy Grace Roman Space Telescope, formerly known as the WFIRST mission, scheduled for launch in the mid-2020s. While it shares some scientific objectives with JWST, particularly in the realm of exoplanet detection and dark energy studies, Roman will focus on a wider field of view and operate primarily in optical and near-infrared wavelengths. Roman's primary focus will be on the study of dark energy, one of the greatest mysteries in modern cosmology, and its capabilities will allow it to complement JWST's work by mapping the large-scale structure of the universe and observing the distribution of galaxies over cosmic time. Another critical addition to the future of space exploration is the European Space Agency's ESA Ariel mission, slated for launch in the mid-2020s. Ariel will focus on studying the atmospheres of exoplanets, building on the data from JWST and other telescopes. With its ability to observe a wide range of exoplanets, Ariel will provide complementary insights into the chemical composition of these distant worlds, including potentially habitable exoplanets that JWST may discover. By studying the atmospheres of these planets, Ariel will help us identify key biomarkers and further the search for signs of life beyond Earth. On the other hand, LUVOIR, Large UV/Optical/Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, are large proposed missions that would focus on studying exoplanets, including their atmospheres, to evaluate their potential for supporting life. While both missions are still in the planning stages, they highlight the growing emphasis on understanding exoplanets and searching for habitable worlds beyond our solar system. LUVOIR, in particular, will push the boundaries of what is possible with space telescopes, offering an unprecedented resolution across a wide range of wavelengths. As the JWST continues its groundbreaking work in space, the next 20 years will bring even more exciting missions and advancements in space technology. These advancements will revolutionize the way we explore the cosmos, and they will have a direct impact on our ability to study distant worlds, understand the origins of the universe, and even consider the possibility of life beyond Earth. One area that will see significant progress is the study of exoplanets. With advancements in space telescopes and detection methods, we will continue to find more exoplanets, some of which will likely be in the habitable zone of their stars. The upcoming launch of missions like the James Webb Space Telescope's successor or the Exoplanet Imaging Mission, EXIM, could provide us with the ability to directly image exoplanets, study their atmospheres, and even detect signs of life. This ability would represent a major milestone in the search for extraterrestrial life, potentially bringing us closer to answering the age-old question: are we alone in the universe? Another exciting development will be in the field of interstellar exploration. Although still in the early stages, the idea of sending probes to nearby star systems, such as Alpha Centauri, is slowly gaining traction. Projects like Breakthrough Starshot, which aims to send tiny light-powered probes to Alpha Centauri within a generation, could eventually allow us to study exoplanets and star systems beyond our immediate solar neighborhood. While this is an ambitious and long-term project, the technological advancements that will arise from such endeavors could revolutionize space exploration in ways we can scarcely imagine. At the same time, missions to study asteroids and comets will continue to provide valuable insights into the origins of our solar system. Projects like OSIRIS-REx and NASA's Psyche mission to explore the asteroid belt will help scientists better understand the building blocks of the early solar system and the materials that could be used in future space mining ventures. The technological advancements in space exploration over the next 2 decades will make possible a new era of discovery. As the capabilities of telescopes like JWST expand, new innovations in propulsion, materials science, and artificial intelligence will also transform our ability to explore the cosmos. One key area of focus is the development of next-generation propulsion systems. While chemical rockets have served as the backbone of space exploration for decades, they are limited in terms of speed and efficiency. New propulsion technologies, such as nuclear thermal propulsion and electric ion thrusters, could drastically reduce travel time to distant planets and enable interstellar exploration. These technologies would make long-duration space missions, such as those to Mars or beyond, more feasible and sustainable. In addition, advancements in space habitats and life support systems will be crucial as we push the boundaries of human exploration. With the growing possibility of establishing a human presence on Mars or other celestial bodies, new technologies for sustainable living in space, including advanced recycling systems and closed-loop ecosystems, will be necessary to support long-term missions. These innovations will also be essential for ensuring the safety and health of astronauts as they embark on deep space missions. Artificial intelligence, AI, and machine learning will also play an increasing role in space exploration. With the enormous volume of data generated by missions like JWST, AI will be crucial for processing and analyzing this data quickly and accurately. AI-powered algorithms can help identify patterns in the data that might otherwise go unnoticed, accelerating scientific discoveries. Moreover, autonomous systems and robotic exploration will enable us to explore planets, moons, and asteroids with unprecedented precision and efficiency. As space exploration continues to evolve, its impact will not be confined to the scientific community. The technologies developed for space missions often have broader applications that affect everyday life. Many technologies originally developed for space exploration, such as GPS, satellite communications, and advancements in medical imaging, have found important uses in industries ranging from telecommunications to healthcare. In the future, the discoveries made by JWST and other space missions will likely have a profound impact on fields like medicine, environmental science, and energy. For example, studying the formation of stars and galaxies could offer insights into the origins of energy production, while analyzing exoplanet atmospheres may reveal new ways to combat climate change. Moreover, the continued development of space-related technologies could lead to new innovations in materials science, nanotechnology, and robotics, all of which would have significant applications on Earth. Space exploration will also continue to inspire future generations, fostering an interest in science, technology, engineering, and mathematics, STEM fields. The missions that will unfold over the next 2 decades will spark curiosity and imagination, encouraging young people to pursue careers in these fields and contribute to the next wave of technological and scientific breakthroughs. As we draw our exploration of the James Webb Space Telescope, JWST, to a close, we find ourselves standing on the precipice of a new era in space exploration and discovery. The telescope's launch represents not only the culmination of decades of scientific and technological progress, but also the beginning of a journey that will radically reshape our understanding of the cosmos. From its breathtaking images of distant galaxies to its ability to uncover the mysteries of star formation, exoplanet atmospheres, and the early universe, the JWST has opened a new chapter in humanity's quest to understand the universe. Throughout this exploration, we've seen how the JWST has expanded the boundaries of what is possible. It is a tool of unprecedented power and precision, capable of observing the cosmos in ways no telescope before it could. It is the culmination of a global effort, an endeavor driven by the collective will of scientists, engineers, and dreamers who dared to look beyond the horizon and reach for the stars. In studying the birth of galaxies, the evolution of stars, and the atmospheric composition of distant planets, the JWST is not just answering questions, but posing new ones, challenging us to think about our place in the universe in ways we never have before. The JWST's journey has been marked by its innovative design, the remarkable capabilities of its instruments, and the ambitious scientific goals it seeks to achieve. Through its infrared observations, JWST has the potential to peer into the very beginnings of the universe, allowing us to study galaxies, stars, and planets as they were over 13 billion years ago. This ability to look back in time offers unparalleled insights into the formation and evolution of the universe and provides an entirely new perspective on the cosmos. Furthermore, the JWST's ability to study exoplanets in unprecedented detail may one day lead to the discovery of planets with conditions suitable for life. The telescope's mission to search for biomarkers and investigate the potential for habitability on distant worlds holds profound philosophical implications. The possibility of discovering life beyond Earth would not only change the course of scientific inquiry, but also reshape humanity's understanding of its place in the universe. In addition to these scientific milestones, the emotional and philosophical impact of the JWST cannot be underestimated. The awe and wonder it inspires are reminders of the human spirit of exploration and our innate desire to understand the unknown. The breathtaking images sent back from deep space serve as a testament to our collective curiosity and resilience, motivating future generations of scientists and engineers to continue the quest for knowledge and discovery. The creation of the JWST was not without its challenges. The project faced numerous technical, financial, and engineering obstacles, many of which seemed insurmountable at times. Yet the global collaboration of NASA, ESA, CSA, and countless other organizations made it possible. The successful deployment and operation of the telescope serve as a testament to the power of human ingenuity, perseverance, and cooperation. The JWST is a triumph of science and technology, one that will continue to yield discoveries for decades to come. The telescope's mission represents a pivotal moment in the history of space exploration, but it is also part of a larger story, one of humanity's ongoing journey to explore the unknown and answer the big questions about our origins, our future, and our place in the cosmos. From the ancient Greeks who first gazed at the stars to the astronauts who walked on the moon, humans have always sought to understand the universe. The JWST is the latest chapter in this centuries-old story, and it will undoubtedly inspire future generations to continue looking up, asking questions, and seeking answers. The discoveries made by the JWST will not only transform our understanding of the universe, but they will also shape the future of space exploration. As we stand at the threshold of new frontiers, it is essential that we continue to support space research and exploration. The telescope's findings will inspire new questions, new missions, and new technologies, all of which will contribute to our growing understanding of the cosmos. For those who are inspired by the work of the JWST, there has never been a more exciting time to pursue a career in science, technology, engineering, and mathematics. STEM. The field of space exploration is expanding rapidly, and there are endless opportunities for young people to contribute to the next great discoveries. Whether through designing advanced telescopes, developing new propulsion technologies, or studying the distant worlds that JWST will uncover, the future of space exploration is bright, and its potential is limitless. In addition to inspiring future generations, the work of the JWST reminds us of the importance of continued collaboration across borders and disciplines. The success of this mission has shown us that when humanity works together, it can achieve incredible things. The telescope's ability to look deeper into the universe than ever before is a reflection of what we can accomplish when we combine the best of human talent, ingenuity, and determination. The discoveries that will come from the JWST are not just for astronomers and astrophysicists. They are for everyone. The telescope's findings will have far-reaching implications for technology, medicine, and many other fields. Whether through new technologies developed for space missions or insights into the fundamental laws of nature, the impact of JWST will be felt across society. For young people considering their future careers, the fields of space exploration and STEM offer exciting and rewarding opportunities. The next generation of scientists, engineers, and innovators will be tasked with answering the questions that the JWST raises, and in doing so, they will unlock new technologies, new discoveries, and new frontiers. Just as the engineers, scientists, and visionaries behind the JWST were inspired by the challenges of the unknown, so too will future generations be inspired to contribute to the next great leaps in human exploration. The James Webb Space Telescope has opened a new chapter in the story of space exploration, one that will be written in the stars. As we reflect on its mission, its successes, and its future, we are reminded of the boundless potential of human curiosity and ingenuity. The discoveries that will come from this incredible telescope will not only expand our understanding of the universe, but will inspire future generations to continue pushing the boundaries of what is possible. As we continue to explore the cosmos, let us remember that each new discovery brings us closer to understanding the vast, awe-inspiring universe in which we live, and perhaps to discovering the answers to some of the most profound questions about existence, life, and the universe. The journey of discovery is far from over. The JWST is just the beginning, and the future of space exploration is as limitless as the stars themselves.
Thank you so much for watching this video. I truly appreciate your time and attention. If you enjoyed this journey, don't forget to hit that like button and subscribe to the channel for more exciting content. Your support means the world to me and helps me create even more amazing videos for you. Stay tuned, and I'll see you in the next one.